This is the FoxAlien Vasto. It's a 3-axis CNC machine which can mill wood, plastics, PCBs, aluminium and steel. The overall size is 80 cm square and 50 cm high, with a working area of 42 by 43 by 8.5 cm. The Vasto features fully supported linear rails for rigidity, ball screws for accuracy, and it's driven by NEMA 23 stepper motors. The work table consists of aluminium and MDF plates, with T-slots for work holding. The spindle motor is a 52mm 400 watt brushed unit with an ER11 collet, and I measured the maximum speed as 10,380 RPM. Alternatively, 65mm and 69mm spindle holders are provided for the installation of a more powerful router or VFD type spindle motor. The control electronics are housed in a steel case with an emergency stop switch, reset, resume and pause buttons, and a knob to set the spindle speed. On the back there is a power switch and IEC power socket, a USB type B connector for a computer, G16 aviation connectors for the stepper motors, limit switches and the spindle motor, and there's also a connector for a laser, which we'll be taking a look at later. Inside the control box the wiring is very neat. We have the switches and the speed pot, the power supply, 4 DM542 stepper motor driver modules, and then the control PCB with an 80 Mega 328P microcontroller. This is running GRBL 1.1H, which is open source CNC control firmware. Then there is a CH340 USB to serial port chip, an SB232EN driver chip, then 2 buck DC to DC step down devices, and a relay to switch the spindle motor on and off. The control box is connected to the machine by a wiring loom, which runs through cable chains. The machine was supplied in 3 large boxes, which contain the pre-assembled sides and gantry units, aluminium extrusion for the front and back, the Z-axis assembly, some hardware and tools, M-mills and V-bits, a height probe, and the software on a USB stick. The manual covers the machine assembly and software configuration. Okay, let's assemble the machine. The final part of the assembly is to install the cable chains and wiring loom. All of the connectors are labelled. The mains input voltage is set with a switch on the bottom of the control box, and the mode switch is set to spindle. Next we're going to install the software, but before we do that, a quick message from today's video sponsor. PCBWay offers rapid manufacturing services, including high quality, affordable PCB services, CNC machining, 3D printing, sheet metal fabrication and injection moulding. Their CNC machining services are particularly impressive, including 5-axis milling and turning, with a wide range of materials and finishes. To get a quote, Just select the manufacturing process, upload your CAD files, select the material and the options. PCBWay is currently offering 10% off selected 3D printing and CNC machining services and a $5 bonus for new customers. For more information, check the link in the description. The software and drivers can be found on the USB drive. The CH340 USB COM port driver is installed first. Device Manager can be used to find the COM port number and check that the COM port is working correctly. A copy of Candle is included on the USB drive. Candle is open source GRBL control software, which is used to control and send G-code to the machine. The GRBL control Candle directory is copied over onto the computer, and it's run by double clicking the GRBL control candle.exe file. I set the configuration back to default and then selected the COM port. GRBL is in a locked state to remind us to home the machine. The machine homes to the front left. This can be changed in the GRBL settings. The axes can now be jogged, setting the step size and feed rate. We can turn the spindle on. GRBL doesn't control the spindle speed. The speed is set with a knob on the control box. It's a good idea to take a copy of the GRBL settings before making any changes. Typing $$ into the console lists the settings, and then copy and paste them into a notepad document. GRBL $130, $131 and $132 max travel settings were configured. The X-axis set to 420mm, the Y-axis to 430mm and the Z-axis to 100mm. The GRBL $110 and $111 max rate settings were increased to 5000mm per minute. The height of the probe target was measured as 15mm. The height probe button is configured under Service Settings. The default probe script is quite useful, so I copy it into User Button 1 and then modify the probe script to work with the probe target. One of the V-bits was installed in the collet. The croc clip connected to the V-bit and the probe target positioned directly underneath. The probe button is then pressed to zero the Z-axis to the base of the probe target. The Z-axis work coordinate is now 20, so if we jog the Z-axis down 20, the V-bit should just touch the surface of the material. To check that the X and Y axes are square, I mark the start position, jog the X-axis 400 to the right, mark the position, jog the Y-axis 300 upwards, mark the position, jog the X-axis 400 to the left, and mark the position. The A and B distances are measured, and if they're equal, the axes are square. If not, then the Y-axis can be manually squared with the knobs on the stepper motors. The 3-4-5 rule can also be used to check that the axes are square, and also that the axes are moving the correct distances. If not, then the GRBL steps per millimeter settings will need to be calibrated. On this machine, it wasn't necessary. FoxAlien have included some G-code examples on the USB drive. Some MDF sheet was clamped to the table, the Z-axis was zeroed with the probe, the V-bit was jogged to the bottom left hand corner, the 0XY button pressed, and then the G-code was sent to the machine with the send button. Spindle motor is supplied with a 1/8 inch ER11 collet. It's worth buying a set of different sizes, and they can be installed by clicking them into the collet nut. Next, I designed a spoilboard in Fusion 360. The spoilboard was made from some old chipboard, which was clamped to the table bed, and the holes were drilled with an 8mm drill bit. Spoilboard was then bolted to the table bed using countersunk bolts and T-nuts, and a 22mm flat end mill was used to level it. Now that the spoilboard is level, let's have a go at making something. I'm attaching some plywood to the spoilboard with painter's tape and mitre adhesive. Spraying one side with activator and applying CA glue to the other side. This makes for a very strong attachment. I'm going to use a 1/8 inch compression end mill. Compression end mills are designed to cut sheet material cleanly. They have an upcut flute geometry from the tip, converting to a downcut further on. The top of the material is cut with the downcut flutes, and the bottom with the upcut flutes. The axes are jogged to the bottom left hand corner, and the XY axes are zeroed. Next, I'm going to use the probe to measure the material and tape depth. The probe target is placed on the surface of the spoilboard, and user button 1 is selected. This runs a script containing a G38.2 probe command, which initiates the probe to move downwards until it makes electrical contact with the target. The Z-axis is zeroed. Now the probe target is placed on top of the material. User button 1 is selected again. And once the probe has made contact, we can read the depth from the Z-axis work coordinate, which in this case is 3.2mm. The Z-axis is now zeroed on the top of the spoilboard rather than the top of the material. I'm going to cut multiple sheets of plywood, and this means that I only have to zero the Z-axis once. I created a design in Carbide Create. In the job setup, the stock thickness is set to 3.2mm, the Z-axis origin or 0 to bottom, and the toolpath 0 to lower left. For the toolpaths that are going to cut all the way through the material, the depth per pass is set to 2mm, the feed rate is set to 1000mm per minute, and the maximum depth is set to 3.2mm. The G-code was sent to the machine. The job was paused after the first cutout to check the size, and then it was resumed. Moving on to the assembly, the cutout parts were glued together. Using stainless steel dowel pins for alignment. Wires were soldered through the back of some LED tape. And then the LED tape was glued inside the centre section. The back was glued together, and a power socket installed. The front was glued together, More parts were glued to the centre. A mirror was added to the back. Wires soldered to the power socket. And finally a two-way mirror installed in the front. Next, I'm going to make a PCB. The PCB design was created in Eagle. The Gerber and drill files were exported. These files were loaded into FlatCam, and it was then used to create the G-code files. The parameters that I used for the top layer were a cut depth of 0.1mm, feed rate 100mm per minute, and a tool diameter of 0.2mm. The drill parameters were a cut depth of 2mm and feed rate of 50mm per minute. And the board cutout was a cut depth of 2mm at 150mm per minute with an 0.8mm diameter end mill. The G-code for the top layer was opened in Candle. The PCB board was attached to the Spoilboard with tape and glue. And one of the V-bits supplied with the machine was installed in the collet. It's important to check that the V-bit is properly centered. The probe target was clamped down onto the copper. The croc clip was attached to the V-bit. User button 1 was selected to run the probe macro. And then the Z-axis was zeroed, followed by the X and Y axes. The copper layer of the PCB is very thin and the board is not flat. To mill the fine traces on the board, we're using a V-bit, where the deeper the cut, the wider the cut width. So if we're not careful, we can end up with variable trace widths. To avoid this, we can create a height map, which uses the probe to measure the heights in a grid pattern. And when we select to use height map, it modifies the G-code accordingly. Next, the drill G-code is opened. The V-bit replaced with a PCB drill. The Z-axis is zeroed. And the G-code sent to the machine. The cutout G-code is opened. An 0.8mm PCB end mill is installed. The Z-axis zeroed. And the G-code sent to the machine. Next I tested aluminium. An air nozzle mounting bracket was designed in Fusion 360 with bore operations for the mounting holes and a contour operation to cut the outline. I added 2 probe macros to the user buttons, button 3 to 0 in the X direction and button 4 to 0 in the Y direction. The end mill is 1/8 of an inch in diameter with a single flute. It has a DLC or diamond-like carbon coating and can be used without lubrication. The air nozzle was then mounted to the Z-axis, and I created some pocket tests in Fusion 360 with 2D adaptive roughing toolpaths and a 1/8 of an inch single flute end mill. All of the toolpaths start with a 2-degree helix cutting down to the final depth of 2 mm. And then cutting the pockets with different optimal loads and feed rates. As the optimal load increases, the quality of the finish reduces, but these are roughing toolpaths designed to remove material efficiently and then follow up with a finishing toolpath. Also tried cutting steel using a 4mm 4-flute carbide end mill with a titanium aluminium nitride coating. I started with a 2D adaptive toolpath, ramping in with a 2-degree helix down to a 2mm depth, and then cutting with an optimal load of 0.1mm. The whole machine vibrated quite badly at times, so next I reduced the helix ramp angle to 1 degree and the cutting feed rate by half. This sounded worse, and you can see the chatter with the end mill visibly slowing down. I tested some helix ramp angles using boring operations, starting with 0.5 degrees, then 0.25 degrees, and then 0.1 degrees. I settled on 0.5 degrees as the best compromise, and then ran the 2D adaptive toolpath again, this time with a reduced depth of 0.5mm. This gave a better result, but it would be interesting to try it with a more powerful spindle motor. First though, let's have a look at the 40-watt laser that is available as an option for the machine. The 40-watt refers to the power input rather than the optical power output. The laser module contains a pair of 5.5-watt laser diodes whose outputs are combined to provide an optical output of approximately 10 watts. The module fits into the holder in place of the spindle. Switch is set to laser. The laser cable is plugged into the adapter cable, which is then plugged into the laser socket on the control box. The other end of the laser cable is plugged into the laser module, and the power supply is plugged into the adapter cable. I'm using Lightburn as the software. The device's screen should be already displayed, where it can be selected with the device's button. The Find My Laser button is then selected. The software should find the device, which can then be added. The name can be changed, and whether to auto home the device at startup. In the Edit menu, under Settings, we can set the units, and under Edit Device Settings, select Enable Z-Axis, Optimize Z-Moves, Enable Laser Fire button, and Laser On when framing. Also check that the S value is the same as the maximum spindle speed set in GRBL, which in this case is 10,000. In the Move tab, the Get Position button is used to display the axis coordinates, which are negative, but Lightburn operates with positive coordinates, so we need to set up an offset. Lightburn suggests setting up two macro buttons. The first to use the laser. $32 equals 1 sets GRBL into laser mode. $10 equals 0 sets the GRBL reporting, and G10L2P1 sets the 3 axes offsets. The second macro button is to use the CNC. $32 equals 0 switches off laser mode in GRBL. $10 equals 3 sets reporting back to the default Vasto value, and G10L2P1 X0Y0Z0 removes the axes offsets. To use the laser, we select the Use Laser button, select the Move tab, and select Get Position. The coordinates are now zeroed and we're working in positive space. We can jog the axes, press the Shift key for big steps, and the Control key for small steps. We can move directly to a position, the laser is focused by moving the Z-axis so that the spacer bar just touches the corner of the laser module. This is a bit tedious, and there is an easier way to do it by using the probe. Another macro button was created called Probe Z, and I pasted in a macro script that I created earlier. What this macro script does is to initiate a G38.2 G-code probe command, apply a G92 command to set the current Z-axis height, and then move the Z-axis to the 0 height to focus the laser. This relies on the fact that the brass end of the laser is electrically conductive, and that there is electrical continuity with the mounting screw. So if we select the Probe Z button, the Z-axis will move down until the laser head touches the probe target, and then the Z-axis moves up to 0, which is the focus height. I'm using a baking rack as a cheap alternative to a honeycomb or pin board. The material is 3mm or 1/8 of an inch plywood. First, the Z height is set with a probe, which can be checked with the gauge bar. The laser is jogged to the bottom left hand corner of the material. Power level of the laser fire button is set. And then the fire button is selected to help position the laser accurately. I'm going to run a power test from Lightburn with a file created by an online tool with a power range from 10 to 90% and a speed range from 50 to 300mm per minute. The file is opened in Lightburn. Unfortunately it's upside down. That's easily fixed. I'm also going to get rid of some text and change the font size. The frame button shows where the laser is going to cut, and we can send the G-code to the machine with a start button. I ran the power test again, narrowing down the power and speed ranges, and I also tried using the air nozzle to provide air assist. That did improve the cuts a bit, but a properly designed air assist nozzle would be a good idea. Next I ran a kerf width test with a 90% power and a speed of 200mm per minute. The laser has a fine kerf width, so I don't need to apply a kerf width offset. So with those settings, I imported a design that I'd previously created and sent the G-code to the machine. I made a mistake and forgot to select the use laser button. The machine isn't operating in laser mode, and that's why the laser isn't turning off between cuts. With the use laser button now selected, the rest of the parts were cut out. Now let's upgrade the spindle motor. I'm going to use a 1.5 kilowatt VFD or variable frequency drive powered unit with an ER11 collet and water cooling. The spindle has a speed range of between 8 and 24,000 RPM, and initially it will be manually controlled. The diameter of the spindle is 65mm, so we can use the 65mm holder that was supplied with the kit. For the cooling, I'm using a bucket, water pump, tubing and deionized water. Now let's try cutting some aluminium. I'm using a 1/8 of an inch single flute bit with a DLC coating. Next I tried a 6mm 3-flute carbide end mill. And then I created a design in Fusion 360, starting with a 2D adaptive roughing toolpath. Then a 2D pocket finishing toolpath. And finally I deburred the edges with a chamfer toolpath and a V-bit. Next I tested some brass. And then steel using a 4mm 4-flute carbide titanium aluminium nitride coated end mill. I created a design in Fusion 360 with a 2D adaptive roughing toolpath. Then a 2D pocket finishing toolpath. And finally a contour toolpath to cut a slot around the part. Okay, so that's the FoxAlien Vasto. The machine features linear rails and ball screws, and it's easily capable of milling aluminium, even steel. In terms of improvements, the supplied spindle motor is okay, but the machine benefits enormously from a more powerful spindle upgrade, and also the table bed rigidity could be improved by adding cross bracing between the slats. Overall, it's a very capable machine. I've tested it over several months, and I'm very happy with it. If you'd like further information, the link is in the video description. Thanks for watching, and see you again next time.